In the previous video, we looked at the trapezoid rule in great detail. Now we're going to look at the Simpsons rule, which is very similar in its development to the trapezoid rule. The Simpsons rule is more accurate because we are going to be using a second order polynomial to approximate the unknown function. However, we will go through this pretty quickly because all the fundamentals have been discussed when we went through the development of trapezoidal rule. In the previous video, we saw in great detail how we can evaluate integrals numerically using simple interpolating polynomials. We discovered all the issues in great detail. For example, we looked at the concept of local error and global error. We looked at how several trapeziums can be put together to get the value of the integral over the whole range for which we decide to find the value of the integral. So all the basic principles have been explained. Here we are going to look at Simpson's rule, which leads to more accurate values for the integrals we are seeking to evaluate. But the principles are all the same. So I'm not going to be going through all the detailed calculations. We are going to go through this fairly quickly, and I hope you will work out the details yourself. The slides will have all the details for you, and I will go through them fairly quickly, but I will not go through the algebra in great detail because the principles are, as I said, they are exactly the same as we did for trapezoidal rule. Now, what is Simpson's rule? Simpson's rule comes about when you're using a second order interpolating polynomial. Trapezoidal rule was for a first order interpolating polynomial. Now, because it is second order interpolating polynomial, which is going to be used here, we need three data points, right, to illustrate the ideas. So the three data points we're going to consider are x0, x1, and x2. So we're going to integrate the function based on values x0, f0, x1, f1, and x2, f2. So we seek this integral x0 to x2 f of x dx. How do we develop an expression for this? Since we have three data points and we have decided to use a second order polynomial p2, f of x can be broken down into p2 plus a residual. And then we can integrate the p2 polynomial, we can integrate the residual separately. Now dx can be replaced by h d alpha as usual. The limits of the integral on the right hand side terms are going to be between 0 and 2. In trapezoidal rule, we just considered two data points and we used p1, and the integration was from x0 to x1. That was the most fundamental unit. Here, the integration goes from x0 to x2, and we know x2 is equal to the reference point x0 plus 2 times h. Therefore, alpha is equal to 2 when x is equal to x2. Therefore, the upper limit of the integrals should make sense to us. Now, what is P2? P2 is this: the constant term, the linear term, the second order term. So the three terms in the square bracket from here. Of course, we know we are going to replace the symbol m minus 1 by n. Okay, whether we call it n or m minus 1, it's all the same as long as we are consistent on both sides of the equation. So anyway, these are the three terms which you can easily recognize that we are using here. And when you integrate this term by term, this is going to yield alpha. This is going to yield alpha squared by 2 times delta, of course. This is going to yield alpha cube by 3, because alpha squared, when you integrate, it's going to be alpha cube by 3 minus alpha. If you integrate, you're going to get minus alpha squared by 2, and then the whole should be divided by 2. This multiplied by delta squared. Of course, f naught, h, etc. are all there. So when you do that and do the algebra, that means you're expanding delta f naught, you expand delta squared f naught, and then put them all together, you will get this expression. And for the residual term, OH3 multiplied by h, so it becomes order of h to the power of 4. Integral d alpha from 0 to 2 will give us 2. So 2 times order of h to the power of 4 is order of h to the power of 4. So this is the local error because this is based on only x0 to x2. This is the error we get. And since we have a h by 3 here, This is called Simpsons 1/3 rule. And I want to mention a subtle point to you before we go further. Suppose we had included the next term. That means we went for P3 instead of P4, because nothing stops us from having as many terms as we want in the Taylor series expansion. So let us say I went and included alpha into alpha minus 1 into alpha minus 2 by 6, that means 3 factorial delta cube, and if I integrated this hd alpha, of course, from alpha is equal to 0 to alpha is equal to 2. If I went ahead and did this, I would have gotten 0 for the limits 0 to 2. That means even if I had an extra term there, I would have got exactly the same expression. Okay, so what's the great deal about this? The great deal about this is, if I had included that extra term, this local error would have been of the order of h to the power of 5. Because the function, if you had included that extra term inside the square brackets, f of x would have had the error of order of h to the power of 4. So when you integrate it with hd alpha, right, instead of dx it is hd alpha, you're going to get this term to be of the order of h to the power of 5. So the local error is really order of h to the power of 5, even though we included only 3 terms in this expansion. So that is a very subtle point which is quite useful for us, because order of h to the power of 5 is much better than order of h to the power of 4. So we are getting something free here. All right. So for the local unit from x0 to x2, this is the value of the integral, approximate value of the integral, and we have computed that the local error is of the order of h to the power of 5. So if someone wanted the detailed derivation for what I said in the previous slide, here it is, right? So I worked out the details, so I leave it to you to go through it. Now, this expression is given for the entire integral from a to b, that means from x0 to xn over the n plus 1 data points. And here we are going to assume that we have odd number of data points. How do we get this result? We know how we get the global error to be of the order of h to the power of 4 if the local error is of the order of h to the power of 5, because we are accumulating many such order of h to the power of 5 between x0 and x2, between x2 and x4, between x4 and x6, etc. So when you accumulate all of those local errors in order to get the global error, we are going to get the global error to be higher. Therefore, it is of the order of h to the power of 4. Now, how do we get this expression? You can understand that integral from x0 to xn. I'm not showing what exactly we are integrating here because you know that. So what I'm presenting here is just a concept, right? So integral from x0 to xn can be split into integral from x0 to x2. So this uses 3 data points, x0, x1 and x2. Then to that, you add integral from x2 to x4. That means x2, x3 and x4 are utilized. And we go all the way till xn minus 2 to xn. That means it is based on the integration between data points xn minus 2, xn minus 1 and xn. So we have n by 2 integrals. This is the data set which goes from x0 to xn. And the integral segments, as I've indicated in a different way here, are from x0 to x2, x2 to x4, x4 to x6, and xn minus 2 to xn. So there are n by 2 parts. And if you want to have n by 2 parts, then n should be even. Otherwise, n by 2 will not be an integer. So if n is even, n plus 1 is odd. Therefore, we should have odd number of data points. Under that condition, you have n by 2 integrals. So the first integral will give us this result as we have just demonstrated here and as we have written in the previous slide. This is the second integral. It is based on x2, x3 and x4. Therefore, you can understand why we get this result and so on. So if you put it all together, you will get this expression h by 3 times f0 plus 4f1 plus 2f2 plus 4f3, etc., etc. And the last 3 terms will be plus 2fn minus 2 plus 4fn minus 1 plus Fn. So you can see a few things here. One is the common term is h by 3. So this is still Simpson's one-third rule. It is valid whenever we have odd number of samples or data points. We can readily apply the Simpson's rule. If you had even number of data points in your table, then we have to have a combination of Simpson's one-third rule with trapezoid rule or some other things, right? So there are many ways of doing it. But if you just focus on purely Simpson's one-third rule, it is readily applied when you have odd number of data points. So that's one thing. Now, if you look at what is inside the brackets, like trapezoid rule, you can see that the starting data point and the end data point, for which the f values are f0 and fn, they appear with weight equal to 1. So it is like one f0 and one fn. But f1, f3, f5, f7, etc. appear with a weight of 4. And terms such as f2, f4, f6, f8, all the way till fn minus 2 come with a weight of 2. So the weights we give to the different data points in our table in the calculation of this integral are different. But please understand the pattern. The first data point and the last data point have weights of 1 each. In the middle, it alternates as 4, 2, 4, 2, 4, 2, and the last but one data point has a weight of 4. So for the middle data points, it is something like 4, 2, 4, 2, 4, 2, and 4, 2, and then 4. This is for the internal data points. So this slide tells us the proof that if you had integrated that fourth term between 0 to 2, you would get the value of the integral to be 0. I just used int command in MATLAB to just show that you can set up a function which is alpha times alpha minus 1 times alpha minus 2. I've just used the symbol a instead of alpha, and I integrate that function which is alpha into alpha minus 1 into alpha minus 2 between the limits 0 to 2, and the integral comes to be 0. So that is reason why the Simpson's one-third rule does not change even if you went for the fourth term inside the square bracket. When we have even number of data points, you can get what is called the Simpson's 3/8 rule, which has similar error properties as the Simpson's one-third rule. So if you had even number of data points, we know Simpson's one-third rule is not applicable totally. You can apply it for a part, but then you must add a trapezoid rule for at least one of the trapeziums. But if you insist on Simpsons for the entire range, even if you have even number of samples, then you have to adopt the Simpsons rule, the formula for which is given here. The global error is still the same as Simpson's one-third rule. You can see a 3/8 h here. So that is the reason why this is called a Simpson's 3/8 rule. And if you look inside, the weights are not the weights you had in the Simpsons one-third rule. So you have a different pattern. One pattern is this: the end points have weight of 1. The middle points have weights such as 3, such as 2, etc. So basically, how is this derived? You use a third order interpolating polynomial by considering 4 data points: x0, x1, x2, and x3. And we know 4 data points are even number of data points. So you consider a third order interpolating polynomial, which you can determine if you have 4 data points. So have 4 data points, which is x0, x1, x2, and x3. And then you develop an expression for that unit from x0 to x3. Then apply it to the next unit, which comprises of x3, x4, x5, x6, etc. I will show something in the next 2 slides, but after that, I also would like to request you to go through this file that I will post on the website. Kindly read it so that you may have some of your questions answered. Now, this is the development. This is x0 to x3, and the dots are the data points that you can also see in the table. So this point corresponds to f0, this point corresponds to f1, this is f2, and let's say this is f3. So this axis is f of x, and the horizontal axis is x. So we have data at 4 points: x0, x1, x2, x3, all equidistant. So we are going to include 4 terms because we are going for a P3 polynomial. please note that this will give you a cubic in alpha. So it's a third order polynomial in alpha. So basically these things we have seen. The error is going to be of the order of h to the power of 5 for the integral, because for the function, the error is going to be of the order of h to the power of 4. So therefore, if you integrate it, you will get the local error to be of the order of h to the power of 5. And if you take this P3 and you integrate it, that is what I've shown here. Now you have to integrate between the limit 0 to 3, not 0 to 2, but 0 to 3, because we are looking at x0 to x3. And x3 is x0 plus 3h. So x0 plus h will take you to x1, x0 plus 2h will take you to x2, x0 plus 3h will take you to x3. So alpha will be 3. So if you do that, if you're patient with the algebra and if we do not do any mistakes, you will get this expression. So this gives the value of the integral from x0 to x3. And the local error is going to be of the order of h to the power of 5 for the integral. Now, if you had data points like this from x0 to x9, that means we have 10 data points here, x0 to x9. So what I'm going to do is I'm going to construct 3 interpolating polynomials. One from x0 to x3, another from x3 to x6, another from x6 to x9, so that I can cover the entire data range. So this P3, when you integrate, will give this result, as you can see. This one, P3, covering these data points, will give you this result. This will give you this result. It's exactly the same thing. We just have to keep tag of the subscripts, that's all. And each of them has a local error of the order of h to the power of 5. Each of these estimates of the integral. Now, if you put it all together, you're going to get f0 plus 3f1 plus 3f2. Then we have one f3 from here and one f3 from here. So 2f3. Then 3f4, 3f5. Then f6 from here, f6 from here. So 2f6. Then 3f7, 3f8. And then the sole f9. And by now you would have collected 3 terms of the order of h to the power of 5. So in general, this accumulation of errors will lead to a global error of h to the power of 4, because we are collecting many local errors. So the error will grow, and from the local error of h to the power of 5 order, it will become a global error of the order of h to the power of 4. So here the weights are 1 and 1 for the terminal points on either side. Then the pattern is 3, 3, 2, 3, 3, 2, etc. And it will finally end with 3, 3. Okay, so I'm talking about the terms in the middle. So you can work it out. You can work out these details. A little bit of work sitting on your desk and trying a few scenarios will help. I'll stop here before we embark on other topics that can serve to improve the accuracy of these methods. Thank you.